Thus far in college algebra, we have talked about constant functions, where we have a horizontal line, linear functions, where there is a slope and y-intercept, absolute value functions, quadratic, square root, cubic functions, even cubic roots and beyond, reciprocal, inverse, or rational type functions. Now we're going to focus our efforts on logarithmic and exponential functions in this unit. Let's move to slide 2 here, where we can actually define what is a logarithmic function and exponential function. Let's start with the exponential functions. This time, our base is going to be a number where the number has to be greater than 0 but not equal to 1. Typically, we have had our number be in the exponent. However, now it's going to be our base itself. Here are some properties of our exponential functions. The domain is all real numbers. So in both of the examples in the pictures below, we can see that they go from negative infinity to positive infinity. Similarly, our range, however, there is a horizontal asymptote at y equals 0. So our range goes from 0, not included, to infinity. 0, 1 is on the graph of our function, and we have a horizontal asymptote. This is 1 to 1, so it passes the horizontal line test, which means that there is an inverse, and we'll talk about that in a moment. It's continuous, so there's no holes or jumps, and it is a smooth graph, so there is no jagged edges, sharp edges, if you will. Now, the way in which our domain and range can certainly change depending upon if we are moving our function about the axis, so if we are transforming our function itself, so keep that in mind. If our base is larger than 1, our graph will look something similar to below. It will always be increasing as x is approaching negative infinity to the left-hand side. Notice that our graph is approaching 0 from the top side of 0. Further, as x is approaching positive infinity, our function is approaching positive infinity as well. If our value of our base is a fraction between 0 and 1, our graph will always be decreasing. So as our x values move to negative infinity, our y values move to positive infinity. As x is approaching positive infinity, this time our graph is approaching the horizontal asymptote of 0 from the top side, and will look something similar to this. Let's move to slide 3, where we can look at an example. Notice that we have our function v of x is 25 times 4/5 to the x power. The value of a car can be modeled by this function, where x has to be greater than or equal to 0 and is the age of the car in years, where v of x is the value in thousands of dollars. Just taking a look at the components of our function here. Taking a look at our function here, we have 4/5 as our base. Notice that 4/5 here is between 0, our base, and 1. So therefore, we are going to be decreasing. Again, v of x represents the value, and x is representing the age. So it shouldn't surprise us that when I see my graph below that it is decreasing because of our base is a fraction. Let's find and interpret v of 0. When I substitute 0 years into my function, what will we expect? So I'll take 25 times 4/5 to the power of 0, which is 25, since anything to the 0 power is 1. And this is in thousands. This represents then 25,000. This tells us that when we purchase this vehicle, at its base value would be 25,000. It is not a coincidence then that here we see that as a y-intercept within our graph. Find and interpret the horizontal asymptote. So as x is approaching, so as the years are approaching infinity, the value of our vehicle is approaching 0 from the top side. So the value of our car is approaching 0 from the top, but it's never going to actually reach a value of $0. Let's move and actually apply this when we're looking at logarithms. What I like most about logarithms is they're another way to write exponents. Logarithm is the inverse of an exponential function. Is log base b of x, read as log base b of x. The common log is when we have 10 as our base. Typically, we do not write the base when it is given as 10. We assume that it is there. We also have what's called the natural logarithm. If our base is e, this is the same as saying the natural log of x. We can have similar properties of logarithmic functions, and I have their pictures on the right-hand side. The domain of logarithmic functions, notice, is the range from our exponential function. And the range of our logarithmic function was the domain of the exponential function. This goes back to our unit on inverses because they are the opposite of one another. Similarly, since it is the inverse, instead of 0, 1 being on the graph, the inverse would have 1, 0 on the graph. Also, x equals 0 is a vertical asymptote. It's also 1 to 1 since it passes the horizontal line test, continuous and smooth. We have some other properties that we're going to utilize a lot in the upcoming sections. I can say that base b to the a power is equal to c if and only if log base b of c is a. What this means then is that I can convert between exponential and logarithmic function writing, and we're going to see that in action pretty quick here. Also, if I have log base b of b to the x power, this is the same thing as x by itself. Similarly, if I have base b to the power of log base b of x, they kind of cancel one another out, if you will, and we're left with x itself. Take a look to the right. If they have a base of our logarithmic function is greater than 1, or if our base is a function, and take a look at those graphs for a moment. Let's head to slide 5 where we can actually do some stuff. Rewrite the exponential or logarithmic equation as its opposite. So if it's exponential, we're going to write it as a logarithm. If it's logarithmic, we're going to write it as an exponential one. So that's going to utilize, back on slide 4, we're going to utilize the fourth bullet down there. The b of a, b to the power of a is equal to c if and only if log base b of c is a. So going back and forth, converting between the two different styles. Right now I have log base 3 of 1 over 81 is equal to -4. So this is written in logarithmic. I'm going to write it in exponential. Notice my base is 3. So my base in my exponential will be 3. I take it to 3 to the power of -4 is equal to 1 over 81. I can verify that this is true because 1 over 3 to the 4th power is the same as 3 to the -4th, which is also equal to 1 over 81. Let's try another logarithmic one here. Notice I have log 100 equals 2. There's no base written, but remember, if there is no base written, we assume that it is 10. So writing this logarithm into exponential form, we'll have 10 to the power of 2 equal to 100, and I can see that this is a true statement. Let's look at C. I have the natural log of 1 over the square root of e is equal to -1/2. Remember, the natural log is the same as saying log base e of 1 over the square root of e equal to -1/2. So I can take then e to the power of -1/2 is equal to 1 over the square root of e. I know if I rewrite this a little bit here, I can rewrite this as 1 over e to the power of 1/2, utilizing our radical rules from the previous unit. I know 1 is on the inside and 2 is my index. So this would be the same as 1 over the square root of e to the first power. Let's move to looking at exponential equations and writing them as a logarithm. 4 is my base, so I'm taking 4 as my base. This is the same thing as saying log base 4 of 32 is 5/2. So going backwards. E looks a little complicated, but 4/5 is my base of my exponential writing. This can then be log base of 4/5 of 5/2 is equal to -1/2. So just converting back and forth. Depending upon what we're doing, one sometimes is easier to utilize than another. Let's head over to slide 6, where we can simplify the following. So right now I have all values that are listed in logarithms. Remember, we can rewrite logarithms very easily as exponents, and I guarantee that we are much more comfortable with exponents than we are logarithms. So I'm going to transpose this into, I'm looking for what does this equal then? Well, transposing it into an exponent, I'm asking base 3 to what power gives me 81? Well, I know that 3 to the 4th power, perhaps by trial and error, just guess and check. 3 to the 4th power is equal to 81. Therefore, log base 3 of 81 is 4. Let's try another one. Here I have log base 2 of 1/8. My base is 2, so writing it in exponential form, 2 to what power will give me 1/8? I know that 2 to the 3rd power is 8, but I need 2 to the -3rd power so that I have 1 over 2 cubed, which gives me 1 over 8. Therefore, log base 2 of 1/8 is equal to -3. Log base square root 5 of 25 is what? So again, we'll write this into exponent form. The base of the square root of 5 to what power is going to give me 25. We might have to do a little guess and check here. I ultimately know that if I were to take the square root of 5 and square it, that would eliminate my square root, but I would still be left with 5, but I need 25. What if I took the square root of 5, squared it, and then squared it again? Well, the square root and the square would cancel, leaving me with 5 squared, and I know 5 squared is 25. Remember, when we have a power to a power, we multiply those powers together. Therefore, log base square root 5 of 25 is equal to 4. Let's look at the natural log of cube root e to the second power. Remember, the natural log is the same thing as saying log base e of cube root e squared is what? All right, I'm going to rewrite this then as e to what power will give me cube root e squared. Remember, we can rewrite this as an exponent, e to the inside value over the index. In order for these to match, our question mark must be 2 over 3. Therefore, the natural log of the cube root of e squared has to be 2/3. So converting back and forth and understanding what it means to be an exponent certainly are helpful in these situations. Let's try some more on slide 7. Log of 0.001 is equal to what? Remember, we don't see a base, so we assume our base is 10. So I'm asking 10 to what power will give me 0.001. This is the same as 1/1000th. So 10 to what power is equal to 1/1000th? I know it's going to have to be a negative, and in fact it has to be -3. 10 to the -3rd power would be equal to 1 over 1/1000th, which is the same as 0.001. Therefore, log of 1/1000th is equal to -3. F and G are written very similar to the other rules that were listed on one of our first couple of slides. I have base of 2 to the power of log base 2 of 8. Notice our bases are the same, so our ending result is 8. They end up almost canceling one another out, undoing each other since they are inverses. Exponential and logarithms are inverses of one another. This next one is slightly different because notice we have a negative in our exponent. So although 117 of our base is the same, we have a negative exponent. That negative exponent tells us that we're simply going to move the whole thing into the denominator. By doing so, everything is positive now. We still have the same base, which undo one another. So this is then 1/6. Let's take a look at slide 8 so that we can practice finding the domain of a couple of examples. Two things that are going to affect our domain, our x values, is if we are shifting left or right, and potentially a reflection across the y-axis. So as I'm looking at 2 log of 3 minus x minus 1 here, first of all, I do know that I have a base of 10, even though it's not listed. I know that the parent function of a logarithm just by itself without any transformations is 0 to infinity. However, I can see with my graph here that that is not the same. Let's first rewrite our new transformed function as f of x is equal to 2 times log of negative x plus 3 minus 1. I'm also going to transform inside so that it becomes, so I can look at it a little more easier with respect to transformations, because there's a couple of things happening. This is also the same as 2 times log of negative 1 times x minus 3. Where this negative 1 calls us and gives us the shift up or down, but we know up or down is only going to affect the the range. We're not interested in the range here. The 2 on the front is going to affect expansion or contraction. The negative 1 here is what's going to reflect across the y-axis. But before we reflect across the y-axis, we're going to look at our shift left or right. This negative on the inside of our function tells us that we're going to shift right 3 units. So if that were to happen without the y-axis reflection, if we shift right, our domain then would move to 3 to infinity from our parent function. But then we're then going to reflect across our y-axis. So when we're reflecting across our y-axis as the second transformation, that means that our domain will have to be from negative infinity to positive 3 because it's reflecting across that y-axis. So we originally would be going this way, but because of the reflection across the y-axis, which means we're flipping to the left, our domain is flipping clear across. Okay, so our domain is from negative infinity to 3 because of the transformations that we just discussed. Let's look at finding the domain of a linear function. Here we have the natural log of x over x minus 1. The domain of a natural log, which we know is log base e, is from 0 to infinity when going back to our logarithm properties. However, we have a critical value. We have an issue because inside our function, we have a denominator we know we need to avoid. So we know x cannot be 1. This is a critical value for us. We also need to find our other critical value for where our entire piece as a rational function is equal to 0. We also have to keep in mind when we're looking at our values that we are greater than 0. We'll talk about that in a second. I can multiply both sides by x minus 1. So I have x is still equal to 0 for a second critical value. Our critical values then are 0 and 1. We have to be greater than or equal to 0. So we're looking for positive values. Notice that 0 is not included, so we are not going to be able to include it within our checking. And we also have to exclude 1 because 1 would give us a 0 in our denominator. We now need some values to check within our function itself. When I substitute negative 1 into our function values here, I end up with negative 1 over negative 2, or positive. When I substitute half, I have half over 1/2 minus 1, or 1/2 over negative half, doesn't matter what it is, negative. And then when I substitute 2 in, I'll have 2 over 2 minus 1, or 2 over 1, which is positive. So we are only interested in our positive values here, and we can see that those certainly are matching the graph of this natural log function. So the domain goes from negative infinity to 0, which ultimately we see is a vertical asymptote associated with the domain of the original natural log. And we're skipping over a bunch, and we're going from our other vertical asymptote of 1, which is associated directly with our denominator, so 1 to infinity. So a little bit of algebra to match exactly what we are seeing within our graph on the right-hand side.